Today our discussion will be on general characteristics of the compounds of the alkaline earth metals. So we are going to discuss about the general characteristics of the compounds. Okay. The dipositive oxidation state of M2 plus is the predominant valence of group 2 elements. So these alkaline earth metals, they usually exist as dipositive, okay, oxidation state. That means M2 plus state, okay, that means 2 plus oxidation state, okay. They usually, we know that their electronic configuration will be NS2, so they will readily lose these 2 electrons and become M2 plus, okay. So they usually exist as M2 plus. Now I've written down these things, okay, in order to save time, okay. So if I explain as well as write down, it will take much time. Now, alkaline earth metals forms compounds which are predominantly ionic, okay. So ionic means there will be positive, negative charge, okay. Like BCl2, something like this, okay. B2 plus Cl, okay. BCl, something like this, okay. BCl2 my 2. So here beryllium will be in 2 plus charge, okay. Cl, okay, minus, okay, something like this, okay, in ionic form, but it will be less ionic than compounds of alkali metals due to the increased nuclear charge and smaller size. We know that these group 2 elements or alkaline earth metals, they are smaller than group 1, okay. Since they are smaller, okay, that means they have high nuclear charge, okay. We have discussed about this in our previous video, why they have high nuclear charge, okay, because of smaller size, okay. And why they have smaller size? Because they have more number of protons, okay. And because of more number of protons, the size, okay, the power of this nuclear charge increases and the size compresses. That means the size becomes smaller, okay. So this is the reason why they are less ionic, okay. Less ionic means the tendency to donate, okay, donate electron will decrease, okay. So only after donating electron they will become M2 plus, right? So it will become, since the size is smaller, it will become harder for them to readily, okay, or easily donate these 2 plus 2 electrons, okay, then alkali metals, okay. That means group 1 element, okay. It will be harder for them, okay, to donate or to lose their 2 electron compared to group 1 element. That is the reason why they are less ionic than group 1. The oxides and other compounds of beryllium and magnesium are more covalent than those formed by the heavier and large size members. So we know that smaller cation, okay, smaller cation can polarize large anion, okay. So this smaller cation, okay, it will be Be2 plus Mg2 plus, okay. This smaller, they can polarize and thus it will form a covalent bond, okay. So usually beryllium, okay, mostly beryllium will show covalent bond, okay, and Mg also will show, but to a lesser extent than beryllium. And heavier and larger members, okay, they hardly, okay, or they don't show this covalent nature, okay, or covalent bond because of their large size, okay, because of the large size of their cations. Now the general characteristics of some of the compounds of alkali earth metals are described here. Okay, so now we come to the main point. Okay, the first one is oxides and hydroxides. Alkaline earth metals burn in oxygen to form the monoxide. So in presence of oxygen it forms monoxide, MO, okay, having rock salt structure. Okay, that means they are ionic. Okay, the structure is ionic. So 2M plus oxygen, okay, to give 2MO. Okay, so oxide. Okay, so when there is one oxygen, oxide. Okay, so BeO is covalent in nature. So we have already discussed here also beryllium, it is covalent. Okay, mostly covalent, it forms mostly covalent bond. Okay, now the enthalpies of formation of these oxides are quite high, and therefore they are very stable to heat. Okay, so the enthalpies of formation, okay, involving while formation of these oxides, okay, these oxides are high. Okay, that means high energy is involved here. Okay, and because of that they are stable to heat. Okay, so they are stable, that means at high temperature also they will not break down, okay, easily. Okay, now let's go to next point. This point we have discussed earlier also. Beryllium oxide is amphoteric. Okay, so it can act as acid and base. Okay, that's why except for this beryllium the rest are alkaline earth metals. We have discussed about that. Okay, and this is not except for this because it is amphoteric. Okay, while oxides of other elements are ionic. Okay, so this one BeO is covalent. We have discussed that also in our previous point, and this BeO is covalent. The rest are ionic and basic. Okay, so since they are basic, they are known as alkaline also, and react with water to form sparingly soluble hydroxides. Sparingly means slightly soluble. Okay, so MO oxide, okay, metal oxide or alkaline metal oxide react with water to give hydroxide, okay, metal hydroxides. Okay, so the solubility, thermal stability, and the basic character of these hydroxides increases with increasing atomic number. Okay, so the solubility, thermal stability, basic character, okay, of these hydroxides, okay, hydroxide increases with increasing atomic number. As the size, okay, of the element increases, the solubility also increases. Okay, and thermal stability also increases, basic character also increases. See, bigger element and this bigger anion, okay, or bigger cation and bigger anion, they are stable. Okay, they will form stable compound. Now because of that their thermal stability also increases. Okay, their solubility also increases. Okay, and basic character also increases. Next point, the alkaline earth metal hydroxides are less basic and less stable than alkali metal hydroxides. Now for these alkaline earth metals, the hydroxide of these alkaline earth metals, they are less basic and less stable than alkali metal hydroxides. We know that alkali earth metals, they are smaller in size than alkali metal hydroxide. So when they are smaller, okay, their bond is smaller. Okay, this BaOH, okay, this bond between this one, okay, BaOH, this bond is smaller. Okay, that means this is smaller, means their bond is smaller, and smaller bonds means stronger bonds. Okay, so in this case it will not give out this hydroxyl OH. Okay, so base in base this hydroxyl is present. Okay, so because of smaller bond they do not readily give this hydroxyl, or this bond will not break easily. But for larger alkali metal, okay, since the elements are larger compared to alkaline earth metals, their bond will be larger. Okay, so if the bond is larger, that means it will easily break, okay, compared to alkaline earth metal, okay, which have smaller bond. That's why they are less basic and less stable, okay, than alkali metal. Okay, less stable means bond is weak. Okay, now halides. Except for beryllium halides, all other halides of alkaline earth metals are ionic in nature. Okay, so the first point here also, the point here and this one, they are similar. Okay, ionic, okay, except for beryllium. So we have come across, okay, that beryllium shows anomalous property, being the first element in the group. So this beryllium, it will show covalent nature. Okay, the rest of the metals will show ionic, they are ionic in nature. Now beryllium halides are, see here, covalent, okay, and soluble in organic solvent. So please remember that like will dissolve like. Okay, that means polar will dissolve polar. Okay, a polar chemical, okay, will dissolve this polar. Okay, like H2O, it's polar. Okay, since it has slightly negative oxygen, slightly positive hydrogen. Okay, so it will dissolve only polar chemicals. Okay, so this one beryllium, it is non-polar beryllium halides. Okay, that's why it can be dissolved in organic solvents. Okay, example of organic solvents are like benzene, toluene, all those. Okay, now beryllium chloride has a chain structure in the solid state as shown below. So this beryllium has a chain structure. Okay, chloro bridge structure. Okay, it's given here. So in the vapor phase, beryllium chloride tends to form a chloro bridge dimer. Okay, so this is the one. Okay, this is the structure. Let's come to the next point. The tendency to form halide hydrides gradually decreases down the group. So the tendency to form hydrates, okay, halide hydrides gradually decreases down the group. We have discussed in our previous video also that smaller the ions, higher will be the hydration enthalpy. Okay, so that means hydration will decrease down the group. Okay, in the same way here for halides, the hydration, or for halide hydrides, it decreases down the group. Okay, so MgCl with the highest, this water molecule 8H2O, followed by CaCl2 6H2O, SrCl2 6H2O and BaCl2 2H2O. Now the dehydration of hydrated chlorides, bromides and iodides of calcium, strontium and barium can be achieved on heating. So this dehydration means removal of this water molecule. So if we heat, it evaporates, and it can be removed. We can remove this water molecule from this hydrated halides of alkaline metal by heating. However, hydrated halides of Be and Mg on heating undergo hydrolysis. So except for these two, they will undergo hydrolysis. Now the fluorides are less soluble than the chlorides owing to their high lattice energy. So these fluorides are less soluble than chlorides. Let's see an example. Magnesium fluoride. This fluoride, they are smaller. Among the halogen, it is the smallest or the first element, so it is small. And these two combined, this Mg is also small in size. That means it will give a stable compound. And since they will form stable compound, their lattice energy will be higher. So when this lattice energy is higher, they will be less soluble. Now when we move down the group, we are talking about halogen. Halogens like fluorine, chlorine, bromine. When we move down the group for halogen, their solubility increases. The solubility increases. Therefore, because of that, these fluorides are less soluble than chlorides. Owing to their high lattice energy. Now let's come here. Source of oxoacids. The alkaline earth metals also form source of oxoacids. Oxoacids, we have discussed about this in our last previous videos. What are oxoacids? So we won't discuss that here. The first one is carbonates. So carbonates of alkaline earth metals, they are insoluble in water. So these carbonates, we have discussed this in hydrogen also. So this hardness of water, is due to this carbonates, presence of carbonates, and these things we have discussed in that hydrogen unit. So carbonates of alkaline earth metals are insoluble in water. So they are insoluble in water and can be precipitated by addition of sodium or ammonium carbonates to a solution of soluble salt of these metals. So we can precipitate these carbonates present in water also by addition of sodium or ammonium solution. The solubility of carbonates in water decreases as the atomic number of the metal ion increases. So the solubility of this carbonate in water will decrease as the atomic number of the metal ion increases. So CO3 2 minus. So this carbonates, CO3 minus. These carbonates, they are bigger anion. They are bigger anion. They are bigger anion. So because of that, a bigger cation will be require for their stability, okay, to form a stable compound. Okay, so smaller cation and bigger anion, it will be unstable. Okay, but bigger cation and bigger anion, they will give a stable compound. Okay, or they will have a higher lattice, okay, energy. Okay, so bigger cation and bigger anion, they form stable compound, and as a result their lattice energy will be higher, and because of that the solubility of carbonates in water decreases as atomic number of the metal ion increases. That means as the size increases. Okay, all carbonate decomposes on heating to give carbon dioxide and oxide. So these carbonates, okay, decomposes on heating. So when we heat, it breaks to give calcium oxide and carbon dioxide. Okay, this is the oxide. Next point, barium carbonate is unstable. Okay, because of the small size of this beryllium. Okay, so this beryllium is small and this anion is bigger, so they are unstable. Okay, we have discussed that in our previous point. So they are kept in atmosphere of CO2. Okay, because they are unstable. The thermal stability increases with increasing cationic size. Okay, we have discussed this also. Okay, as the size increases, the stability, okay, also increases. So that means they will not decompose easily. Okay, there will be stability. Okay, if the cationic size is bigger. Okay, now sulphates. Sulphates of alkaline earth metals are all white solids and stable to heat. Okay, so for sulphates they are stable. Okay, solid, white solid and stable to heat. Beryllium sulfate and magnesium sulfate are readily soluble in water. See, since they are not stable, okay, that means their lattice energy is small, okay, or low. Okay, that's why they are soluble. Okay, now solubility decreases from CaSO4 to BaSO4. So from smaller to larger cation. Okay, so larger cation and larger anion, SO4 2 minus, okay, Ba2 plus, okay, SO4 2 minus cation. Okay, bigger form stable. Okay, and since they are stable, lattice energy is higher, and that's why solubility decreases. Okay, when the size of the ion increases. Okay, we can say down the group also. Now the greater hydration enthalpy. Okay, so we have discussed this before also. Smaller size means higher hydration enthalpy. So the greater hydration enthalpy of Be2 plus and Mg2 plus ions overcome the lattice enthalpy factor, and therefore their sulfates are soluble in water. So that means beryllium sulfate and MgSO4, they have lattice enthalpy, but due to small size of this Be2 plus and Mg2 plus, they have higher or greater hydration enthalpy, and this hydration enthalpy overcome this lattice enthalpy. Okay, and this Be becomes Be2 plus, Mg becomes Mg2 plus. Okay, that means ions is formed. Okay, and when ions are formed, that means they are soluble in water. Okay, that means they are soluble. Okay, because of their high hydration enthalpy, okay, compared to lattice enthalpy. Now nitrates. The nitrates are made by dissolution of the carbonates in dilute nitric acid, okay. That means they are dissolved in nitric acid. Metal carbonate react with 2 moles of nitric acid to give metal nitrate, okay. This is metal nitrate, this one metal nitrate, and carbon dioxide and water molecule. The tendency of metal nitrates to form these hydrates decreases with increasing size, okay, and decreasing hydration enthalpy. So this hydration enthalpy, okay, is formed by smaller ions, okay, and as the size increases, this hydration enthalpy decreases. That means it decreases when the size increases, okay. So the tendency of metal nitrates to form hydrates decreases with increasing size, okay, and as the size increases, hydration enthalpy also decreases, okay. And that is why these metal nitrates, okay, their tendency to form hydrates decreases from MgNO3 to 6H2O, okay, to BaNO3 2, and this is anhydrous, okay. That means no water molecule is present, okay. The water molecule is present, but here it is present, okay. Anhydrous means this, okay, in simple words. All of them decomposes on heating to give the oxide, okay, like lithium oxide. So this metal nitrate, they decomposes on heating, okay, to give oxide, okay, give nitrogen dioxide and oxygen, okay, or dioxygen.